At the poles, it's cold all the time. Polar temperatures influence more parts of the Earth than you might think. These cold regions control the thermostat for the rest of the Earth. Water, ice, and vapor.
Milk?
Water exists as a liquid, solid, or gas, depending on temperature. One way to measure temperature is by looking at the infrared light it emits, light outside the range that's visible to the human eye.
Sugar?
Right here.
Colors in these infrared images represent temperature: blue for cold, red for warm. Satellites that collect infrared images allow us to look at Earth's temperatures on a planetary scale. Bright regions on the Earth, like clouds, reflect sunlight back into space, helping to keep them cool. Here's a different view of the Earth. This is how the planet and clouds look in infrared. Clouds are cold, partially because they reflect the sun's energy and don't absorb much heat. By contrast, open ocean and exposed land absorb sunlight and become warm, shown here by orange and red colors. You can see the land warm during daytime and cool off during nighttime. Now we'll tip the planet to take a look at the poles. Ice behaves much like clouds because icy surfaces also reflect much of the sunlight they receive. This is one of the reasons why the poles stay cold. But the main reason is that they receive less direct sunlight than the rest of the world. The amount of sunlight reaching the polar regions changes with the seasons. This globe shows the Earth in July. Tilted away from the sun, the colder South Pole, in purple, hides in shadow, while the warmer North Pole, in pale blue, basks in a long day of summer sun. During winter darkness, frigid temperatures freeze the surface of polar oceans down to a depth of several meters. This is sea ice, expanding during the fall and winter, shrinking during the spring and summer, a timeless presence floating on the ocean's surface. But is it eternal? More than a quarter century of satellite data reveal a substantial decrease in sea ice at the North Pole. Less ice means the Earth has a smaller reflective surface to bounce sunlight back into space. Less ice also means there's more exposed dark water to soak up the warming rays of the sun. The Earth warms, leading to faster melting and additional ice loss. This feedback loop means the poles amplify temperature changes around the world. Most atmospheric water vapor comes from ocean evaporation. Water vapor forms clouds in the atmosphere. Clouds return water to Earth in the form of rain and snow. This cycle, water drawn up from the oceans and falling from the clouds, delivers almost all fresh water to land. Rain delivers water immediately, but snow stores water and slowly releases it to surrounding land over time. In winter, snow covers up to 40% of the northern hemisphere, replicated here around the sphere. As snow cover recedes in spring and summer, the melting snowpack refills reservoirs and underground aquifers. Without adequate snowfall, freshwater reserves fall, lakes shrink, crops fail, deserts spread. Even when snow recedes, land in some regions of the world stays frozen, even through summer. Permanently frozen land, called permafrost, occurs at both high latitudes and high altitudes. Permafrost covers 25% of the northern hemisphere and can reach a thickness of more than a kilometer. Thawing permafrost causes buildings to collapse, roads to fracture, and trees to uproot. But far more serious consequences arise when permafrost thaws and releases significant amounts of methane. Methane is a byproduct of decomposing plant and animal remains, previously held in suspended animation for thousands of years. It's a potent greenhouse gas, much more so than carbon dioxide. Increased methane levels inhibit heat from escaping Earth's atmosphere, amplifying the warming trend. Snow that doesn't melt from year to year compacts into ice, forming ice sheets, glaciers, and ice shelves. Ice sheets are the enormous collected masses of glacial ice that cover Greenland and Antarctica. More than 3 kilometers thick in some places, they contain as much as 75% of all fresh water on Earth. Glaciers are large rivers of ice that move slowly in response to gravity. We find glaciers all over the world, even on high-altitude mountains near the equator. In human terms, glaciers move slowly, from a few centimeters to a few kilometers a year. Even slow ice movement has a large influence on sea level. Billions of tons of ice can crash, slide, or melt into the ocean from glaciers that meet the shore. What's more, many glaciers worldwide are accelerating. Over hundreds of years, glaciers advancing offshore can form ice shelves, massive platforms of ice permanently attached to the glaciers. Ice shelves cover almost half of the Antarctic coastline and some parts of the Greenland and Canadian coasts. They act as dams, restraining glaciers from sliding into the ocean. Several major ice shelves, thousands of years old, have recently disintegrated. The glaciers on the land behind them, suddenly released, now move more quickly into the sea. Ice moving from land into the ocean causes global sea level to rise. Consider this experiment. Imagine the Earth with no water at all. This is the whole planet as nothing more than dust, dirt, and rocky ridges. If we fill the lowlands here with as much water as we find in current oceans, we reveal the familiar shapes of the Earth today. Civilization, represented by beacons of light cast into space by the world's cities, has adapted to the relatively constant shape of the world's coastline. Sea level and civilization are connected. Even a small rise in sea level could have a significant impact on the hundreds of millions of people living in coastal regions near the ocean's edge. This thought alone focuses the mind on Earth's delicate balance. Our planet's climate is intimately connected to the frozen parts of the world. Few of us will ever travel to the polar caps or high-altitude glaciers. But every day, the present and future health of Earth's grand, frozen wilderness profoundly affects all life on Earth.